A very good morning. A very good morning to all of you. With great joy and immense pleasure, I feel privileged to extend my warm welcome to each and everyone present here. We have all gathered here this pleasant morning on the third Brother Stanislaus Memorial Lecture commemorating the 105th birth anniversary of the Grand Master. When we speak of St. Paul's High School, we inevitably think of Brother Stanislaus, who steered the destiny of the school for 18 long years and took it to great heights. Brother Stanislaus was appointed as the 5th principal of St. Paul's in the year 1958, and the same year the school was made autonomous. During Brother Stanislaus' tenure, the school attained the name of being one of the best schools in the Twin Cities, winning laurels in academics, bagging state ranks. For the commitment and dedicated service, Brother Stanislaus was honored with the National Award Best Teacher for the year 1970-71 by the then President of India, Sri late B.V. Giri. The massive school buildings standing tall on either side of the road are the pioneering efforts of this visionary. All the old boys of the school hold him in great veneration for uncompromising quality of academic excellence and strict discipline instilled by him. On the 20th September every year, the members of alumni celebrate his birth anniversary, paying rich tributes to the visionary, guide, and philosopher, Brother Stanislaus. Let us begin the proceedings of the day, imploring the blessings of the Almighty. I request the school choir to lead us in prayer. Light symbolizes knowledge, wisdom, and free will. To solemnize this occasion, I would like to welcome our principal, Reverend Brother Rayappa Reddy, Sri S. Mazhar Ali, President, Alumni Association, and Sri Arvind Frederick, Security, Alumni Association, and students of Class 10, Sattu Vahin Reddy and Oditi Reddy, to come forward and light the lamp. Education is the movement from darkness to light. May I now invite Sri T. Nagaraja, Senior Alumnus, and Sri Zubair Madani, Joint Secretary, St. Paul's Alumni Association, to garland the portrait of Brother Stanislaus. Thank you, sir.
A very good morning to all of you. I'm glad to introduce our proud alumnus, Professor Balasubramanian Ananthanarayan, the guest speaker of today's webinar on the third Brother Stanislaus Memorial Lecture, Joy of Discovery, Motivating a Career in Sciences. Professor Balasubramanian is the recipient of Ashwini Memorial Prize as the best outgoing student of class 10 from 1978 batch. He finished his intermediate from Little Flower Junior College, Uppal, and was a state ranker in both 10th and 12th grades. He is a Master of Science and has to his credit PhD in Physics from University of Delaware, USA. He has done his chemical engineering from IIT Madras. Professor Balasubramanian was a former chairman at the Center for High Energy Physics and held the post of MSIL Chair Professor for the Division of Mathematics and Physical Sciences. He was the Chair Professor at Indian Institute of Sciences between 2015 and 18 and has put in 24 glorious years of service to the Department of Physical Science. As a physicist, he sees what everybody sees, but thinks what nobody thinks. His research is in a whole wide range of fields, including effective field theories, beyond the standard model physics, and physics at the proposed International Linear Collider and aspects of mathematical physics. As a keen researcher, teacher, and popularizer of science, he has also written widely for general audience. Presently, he is on the board of editors of the Springer Brief series in physics and the European Physical Journal Special Topics since 2018. St. Paul's is highly elated to welcome you, sir, to this webinar. Dear students, you are privileged to get an opportunity to listen to Professor Balasubramanian today. May I now invite Professor Balasubramanian Ananthanarayan to address the audience.
Thank you very much. It's a very great honor for me to be here, to be giving the third Brother Stanislaus Memorial Lecture. It's an overwhelming moment for me. This is also the first talk that I'm giving in to a general audience since the demise of my father earlier this year and my mother last year. So I would like to dedicate this talk to their memory. I'd like to thank them, first of all, for infecting me with their love for science. After I just gather my emotions, let me begin by thanking Mazhar Ali Ahmad Saab for organizing this invitation, and also thank Brother Rayap Reddy for giving me this opportunity. Brother Rayap Reddy today lives. He's the living symbol of Brother Stanislaus, in whose memory this lecture is being given. I have the slides being shown. May I request the slides to be shown? Yes, thank you.
Just a moment, sir. I'll just doing that.
Yeah. The first slide, please. Yeah. The cover slide.
It's being displayed, sir. Can you see
the first one? Okay, good. So I would like to sort of have a relaxed environment in which we talk about many of the things that I plan to talk about today. I want to actually tell you many stories, many stories to begin with, and then have some questions from you. So in order to actually thank St. Paul's High School for what it has done for me, the best quote that I have is from Alice in Wonderland, one of the poems where the youth says, "Well, you're old, and your jaws are too weak for anything tougher than sweat. Yet you finished the goose with the bones and the beak. Pray, how did you manage to do it? In my youth, said his father, I took to the law and argued each case with his wife, and the muscular strength which it gave to my jaw has lasted the rest of my life. So this is really what I think St. Paul's has done for me, and I'm sure that is what it is doing for all the kids over here. The rigor of the education with which we have had in our early life in the school is what has helped me a lot, and especially the grounding in mathematics and physics and in languages and in all the other subjects. So next slide, please. So the next slide here, of course, shows you the picture that all of you know. This is Brother Stanislaus, and he was, of course, much respected and feared by all of us. And he passed away, I think, when I was in 8th standard, and then Brother Dominic was the next principal that I had. So it's such an honor to be talking about him. Next slide, please. So I want to begin by showing you many pictures of people who have contributed a lot to science, and why they think that we should do science, and in particular mathematics, for instance, and so on. Here is a picture of David Hilbert, who was one of the most influential mathematicians of the late 19th and early 20th centuries. So he had a motto, and this is what I think captures the essence of what we really do in science. And before that, I also want to show you this memento, this wonderful memento that I got from the Alumni Association. And it also records its thanks to everybody who's an involved party in this. So I just wanted to thank the Alumni Association for this also. So let me put this away and then get on with my talk. So the words of Hilbert say, we must know, we will know. So that is the voyage of discovery on which we as human beings have embarked for a very long time. And the joy that it gives us, why does it give us joy? That I do not have an answer for. And that is really the motivation why any working scientist continues in his or her own work. That little moment when you have a revelation is what we want to work for. So that being the basis, I'll try to argue in this talk that it is as good a career as any in order for us to be full-fledged human beings. Next slide, please. So here is a picture of a very important scientist, but she's not very well known. So I just pose a question as to who this is, and probably you will not know, but towards the end of the talk, I'll tell you who it is. She's a very important figure, but practically unknown. So she's probably the sort of person that we have in mind when we talk about doing science and so on. You just pursue the goals of science and the goals of knowledge without worrying too much about what is the kind of fame and the fruit that I will get. So I'll come to this later. Next slide, please. So I want to talk to you about a particular discovery that took place and was announced about 5 years ago. There have been equally important discoveries after that have also been spectacular. But this is a particularly important one which captured my imagination, because we also had a live streaming webinar like we are having today, because it was already announced that such a web streaming would take place. And this is what is called the LIGO discovery, where LIGO stands for the Laser Interferometry Gravitational Observatory. It is an observatory that is based in the US. It is funded by the National Science Foundation. And it consists of 2 different laboratories, one in the state of Louisiana in the south and east of the US, and another in the state of Washington in the north and west. It's an amazing idea which had been proposed many, many years earlier by several scientists. And in this press conference, the principal investigator of this particular project, Professor David Reitzer, his voice was shaking and breaking, and all he could say is, ladies and gentlemen, we have detected gravitational waves, we did it. So I thought that this is an amazing thing, that here is a leader of a collaboration of many hundreds of scientists. And this is the moment that he was working for, that he had worked for such a long time. So what he was reporting there was the results of a very serious experiment that had taken many decades to perfect, based on modern technology, all kinds of scientific instrumentation and teamwork of hundreds of people, scientists, technicians, and so on. So this gravitational waves, which had been predicted by Einstein nearly 100 years ago, was finally discovered by human beings. And the actual signal had been seen by a rather young person. He was a postdoctoral fellow, Dr. Marco Drago, who had seen this prediction of the general theory of relativity made 100 years prior. And this took place very far away, very long distance away. In fact, took place 1.4 billion years ago. Billion here is used in the sense of 10 to the power of 9. That's 1,000 million years ago. So what happened was that far away in the universe, there were two objects that we know as black holes. Today, it's all part of common language, common parlance. It's there in newspapers. These black hole solutions or black holes which exist in nature were predicted by the Einstein theory of relativity. These are enormously heavy objects of the order of 36 and 29 solar masses. And then they merged in a fraction of a second to give a new black hole of 62 solar masses. Now you may say 36 plus 29 doesn't add up to 62, it adds up to 65. So what happened to the other three solar masses? Well, in that flash, in that merger, this turned into pure energy, gravitational energy, and was released in this collision such a long time ago. And this was released as energy, and it shook the fabric of space and time. So that is the kind of thing that we are looking at today in science, the kinds of discoveries that go on in faraway parts of the universe, which requires a lot of theory and experiment for us to really understand what is going on. Now, India will also start to participate in this LIGO project, and there is a project known as Indigo for the Indian part of this LIGO collaboration. It will be built somewhere near Pune, not far from Pune. As far as I know, it is sanctioned. And this, when Einstein wrote his paper, he was aware that such things, that gravitational waves will exist, but he believed that we will never be able to see it because the effects due to gravitational interactions are so small. So this is a spectacular example of what I would think coming together of theory and experiment. And next slide, please. Yeah, the Nobel Prize for this. So here are the pioneers of general relativity and black hole solutions. So that is Einstein seen as a young man. So believe it or not, Einstein was also young once, just like you all. And although pictures of him are typically those when he was over 60 years of age, this was when he was about 26 years. And these are the other two people who had actually worked and showed what black holes were. And this was Carl Schwarzschild, who actually solved Einstein's equations soon after they were written down. And then he unfortunately passed away during the First World War. So he has one great contribution to science. And, you know, he is remembered more than 100 years after his death, tragic death. And the other one, so Schwarzschild found a solution to what we call a static black hole. And the spinning black hole were found by this other person, Roy Patrick Kerr. He lives in New Zealand, and it was an astonishing discovery. Next slide, please. So this is what happened in that instant when these two black holes merged together. And when they merged together, they sent out this ripple in space-time, which we observed on Earth a few years ago. Since that time, LIGO has observed many more, and this has become a precision science. So here is an example of coming together of mathematics, physics, technology, engineering, so many things. That's why I wanted to present this example. Next slide, please. So these are the three people who thought of this experiment and actually carried this out. Rainier Weiss and Barry Barish are experimental scientists, and Kip Thorne is a theorist who had this idea that you can actually build an Earth-based device in order to actually see this, see the gravitational radiation. Now, this suggests that you have to be bald and you have to be, kind of elderly before you win the Nobel Prize. Sometimes that happens. So let us all hope that we live a long time and carry out great discoveries and live to win the Nobel Prize. Next slide, please. So this was one particular example that I brought. But along with this came a new branch of science, of physics. And this is an era in which we live, which is called multi-messenger astronomy. So that, the one that I talked about, was merger of black holes. There are other celestial objects called neutron stars. Neutron stars can also merge. And soon afterwards, LIGO also saw the merger of neutron stars. But neutron stars are pretty active objects, unlike black holes, which are kind of inert. So neutron stars also produce all kinds of other energy when they merge. For instance, they produce light in various parts of the electromagnetic spectrum. And it so happened that when this particular thing was seen, this neutron star merger, immediately many other telescopes were asked to look at that part of the sky because there would be delays in the emission of other parts of the electromagnetic spectrum. And it fitted beautifully. You saw bright blue light, you saw X-rays, you saw all kinds of things. So this is a completely new world in which we live, where you have sophisticated instrumentation, all kinds of instruments, some satellite-borne, some balloon-borne, some Earth-based, some looking at the gravitational sector, some looking at the electromagnetic sector. So it's really an exciting era in which we live. So science has progressed a lot, and it's quite a challenge to keep to keep oneself abreast of the developments. Next slide, please. So this is the timeline today that, human beings, after all these years of thinking about the universe, this is the picture that we put together of where we come from. So all of you have heard of the Big Bang, which is supposed to have taken place. This idea goes back to George Gamow in the 1940s. And later, the cosmic microwave background radiation was found in the 1960s. And today we think that the universe itself, just imagine the project of science, to think about the origins of where every one of us came from, where everything that we see comes from, and things that we don't see either, because there are parts of the universe that we haven't seen yet. So this is the timeline of the universe, which started long ago from the Big Bang, and all kinds of matter formed from the primordial energy. Isn't that a beautiful thing, that today we actually have an idea of where every one of us, everything comes from? So this is something to motivate what the project of science is. The next slide, please. So this is the scales of the universe that we talk about over here. So this is just something that I wanted to show you over here, of where we come from. Right in the middle of this, towards the lower, that spot that you see, it's called a quark. Now, quarks are components of what we call protons and neutrons. And these quarks then form protons and neutrons, which form nuclei. So you can start in the middle of this picture, a little to in the third quadrant, where you can see the quark and how the quark forms an oxygen nucleus, and then the oxygen nucleus. So this is the growth in scales of size that we see, from very small objects to bigger and bigger objects. So from quarks to the nucleus, to a sand grain, and the sand grain then is in a beach, and you can see what roughly the human footprint looks like. So that gives you the scale as it builds up. And then this little beach is sitting on this little planet, the blue spot that we call, the bright blue spot, which is the Earth on which we live. So that is a little beach that is shown, which goes around an ordinary star, a very ordinary star that we call the sun, and it goes around the sun. And the sun itself lies in what we call the solar system, where the biggest planet, Jupiter, is shown over here. And of course, the solar system extends far beyond, up to Pluto. Poor thing was called a planet. It's been downgraded to a dwarf planet. But the solar system even extends beyond. For instance, comets, which go very far away, far beyond Pluto, come back in. And this solar system sits in one of the outer spirals of a galaxy that we call the Milky Way. Akash Ganga, we call in our language, which is called the Milky Way in most European languages. And the Milky Way itself is one of several galaxies that forms the local cluster, which belongs to a supercluster. And then the supercluster belongs to the visible universe with all these huge structures. Now you have to imagine what kind of a project this is and how we have pieced together this picture. So this is the marvelous universe that we live in with all this knowledge. Of course, we as human beings will continue to improve the understanding of science. Next slide, please. For instance, there are many, many pieces of interactions that we are accustomed to, like the electromagnetic interactions, which causes light. And for instance, something called the weak interaction. The weak interaction, for instance, is responsible for nuclear beta decay, for radiocarbon that we use in archaeological studies. So the question is, how come you have these forces like electromagnetic force and something called the weak force, which is a short-range force? So this was a puzzle in elementary particle physics, how such a short-range force could come to be. And I'm sure many of you have read in the newspaper about something called the Higgs mechanism, and the discovery of the Higgs particle. I'm afraid many of the kids in this audience today, they were probably really tiny tots at the time of the discovery of the Higgs particle, but we were all very excited, especially elementary particle physicists. So this was finally discovered about 9 years ago on July 4th, 2012, at an experiment called the Large Hadron Collider, which is at CERN. CERN is the European Nuclear Research Center. But I want to point out certain aspects of this discovery. The existence of this particle was predicted by Peter Higgs, also Nobel laureate, in the year 1964. 1964, very good year. The year of birth of your today's speaker, for instance. That's one good reason why 1964 is a good year. The other being, of course, that Peter Higgs predicted the existence of this particle. You see, it took 48 years since the prediction of this particle and its actual discovery. You need very special experimental conditions in which you can create such particles and test the hypothesis of elementary particles. Peter Higgs was not the only one. There were some other authors also who had worked at that time. For instance, there was another paper by François Englert and Robert Brout and many others. And in fact, the Nobel Prize went to Peter Higgs and François Englert. Robert Brout had passed away, otherwise he would have also been awarded the Nobel Prize because it's a convention not to award the Nobel Prize posthumously. François Englert is from Belgium, and during the Second World War, actually there's a threat that he could have been killed in the various, the disasters that Europe faced. So I think he had even been in hiding. So what I want to bring out over here is that in this enterprise of science, there's also human history. There is also the struggle, the tragedy, the stories of valor, of fighting against all odds in order to make these discoveries. Just something to keep in mind. I'm not saying that human suffering is either a sufficient or a necessary condition for these things, but something to keep us humble, and grounded on earth. So it took many generations of dedicated experiments at ever-increasing energies and increasing precision in order to find, this Higgs particle that I talked about. It is an enormous experiment which actually is conducted at CERN. There is a ring whose diameter is 27 kilometers. Can you believe what 27 kilometers is? That's roughly the distance from St. Paul's High School to Hyderabad Airport. I'm sure all of you know. It's more like 40 kilometers. But anyway, to give you an idea, that's the circumference of this experimental apparatus. Today, we don't just have potentiometers and beakers and pipettes and so on. Of course, you have to do that too in order to understand the scientific method. But the scale is something immense. And this is a point that I will try to discuss in this talk. Next slide, please. So these are the two Nobel laureates over there, François Englert with the tie and Peter Higgs, who did not wear a tie. And this is Rolf Dieter Heuer, the then Director General of CERN, who made the announcement. So this was also webcast, and we also watched it here live in Bangalore. It was another very amazing experience to see this. Next slide, please. Yeah. So I want to dwell here on a couple of aspects of what is scientific discovery tree. Most of the examples that I've chosen are from physics, but this is universal. Physics is something that I can talk about because I'm in this field, but this is actually universal. So what is the nature of scientific discovery and why do we do it? How do we do it? These are the questions. Okay. As I said, from the examples that I've discussed, that some of these areas require massive teamwork and technology for fundamental discoveries. But there are also other fantastic discoveries which are still on tabletop, human ingenuity in the design of experiments, to have a sixth sense and a hunch for where there might be a discovery. And a lot of hard work. As you all know, Edison said it's 99% aspiration and 1% inspiration. That has not changed since the time of Edison, that's for sure. But also fantastic discoveries such as what we call high temperature superconductors. Then there is a material called graphene, which is a certain, based on carbon, as you all know, it has to be from graphite, which is a phase of carbon, just like diamonds. There are objects called topological insulators, which also have many interesting properties. But all these advances are made by single-mindedness and perseverance. So that is the thing. So here, many of you may be wondering, oh dear, all this is so overwhelming. Well, anything is overwhelming, right? So if you have to learn to swim, you have to jump into the swimming pool. You can't just really read books about how to swim. Or if you want to play chess, and keep reading books on chess, but ultimately you have to play. So you may be interested in what is the role of the individual. So let us take up some examples here. As I said, much of what I'm going to say are stories. You have to piece them together, weave the plot, and see how you understand. So this is only to take you there, and after that, it's up to you. So what is the key message of all this? Next slide, please. Let me take an example from mathematics, because it's easy. Mathematics is something that everybody understands, and especially in St. Paul's, I know that all the students are extremely well trained in mathematics, and you will be able to understand this problem. All of you know what the Pythagoras theorem is. Pythagoras theorem says for a right angle triangle, x squared plus y squared, which are the two sides which have the right angle between them, is equal to z squared, where z is the length of the hypotenuse, right? So there are whole number solutions to this. 3 squared plus 4 squared is 5 squared is an example. So this was known to Pythagoras. It was known everywhere. All civilizations knew this because it was very important for land, for keeping track of, how many acres of land you own. So you can't have any dispute. So accurate measurements of sides of plots of land is as old as human history. So the question you can ask is whether you have whole number solutions when the power is not 2. For instance, x cubed plus y cubed is z cubed. Are there whole number solutions to this? Now, this is a question that was posed. Presumably, the question was also posed in antiquity, but we know for sure that this was posed by Pierre Fermat in 1637. As you can see, it will soon be 500 years, when he said that you cannot find such solutions. Now, in mathematics, you need a proof. You can't just say things. And it took more than 450 years to prove that Pierre Fermat was right. Although he made a sentence in his copy of some book saying that I have found a proof, but there isn't enough space to write this proof over here. Now, this was settled only about 25 years ago by Andrew Wiles, who's shown here. Now, Andrew Wiles, when he was a kid like you all, he borrowed a book from his local library where he read about this, and he promised himself that he is going to prove this theorem. Okay, but it was only long after he had made himself this promise that there was a chain of ideas which come again from two Japanese mathematicians soon after the World War. They lived in terrible conditions. They were hungry, all kinds of things that are wonderful, not so wonderful. But anyway, there are stories about the kinds of conditions in which Taniyama and Shimura lived. But they developed a branch of mathematics which ultimately paved the path to the proof of Fermat's theorem. Now, there are two wonderful books on this Fermat's last theorem, one by Simon Singh and one by Amir Axel. They both suggest that next time you want to give a gift to your friends, or your friends want to give you a gift, you keep ordering these books for each other. And he also has given, in a BBC interview, his Eureka Moment, how he found this missing steps in his proof. So this is an example of a great discovery in mathematics. Next slide, please. There's another equally romantic story, sometimes even more romantic, because it also shows how peculiar some mathematicians are. It is generally rumored that mathematicians are very peculiar. It may be because the subject is in a sense difficult. It is also not directly related to your daily experiences. So only people with, a sixth sense or other, other kinds of abilities who can really succeed in mathematics. And I'm sure all of you have all those abilities. Let me promise you that every one of you has those abilities. And it's a matter of developing those abilities and to have the love for this subject. So this was something known as the Pankaray conjecture. Henri Pankaray was a very important mathematician towards the end of the 19th century. His cousin was the Prime Minister of France during the first British family, as you can see. So he posed a question where he said, if you have a surface that is really crinkled, it is as good as a sphere. Okay, so this is the property, loosely speaking, that Pankaray thought that all surfaces should have, irrespective of which dimensions you live in. That's the thing about mathematics. We are used to one dimension, which is a line, 2 dimensions, which is a plane, or 3 dimensions, which is a space in which we live. Now, mathematicians can generalize all these ideas, notions, and have n-dimensional spaces. So he made this series of conjectures that about objects in those spaces and the properties of those objects. Now, he posed this, I think, in 1901 or so, and this was finally proved and settled about 2005. And it was proved by this person whose picture that I show over here, based in Leningrad or St. Petersburg, Gregory Perelman. And it's also an example which can win you $1 million. There's something called the Clay Mathematics Foundation, which has enumerated 7 problems. And if you solve them, you can earn $1 million. So if you want to become a mathematician, sometimes you can also earn a lot of money. Out of all these 7 problems, only one has been settled so far. And it was this one. And to make it even more complicated, he refused to take the prize. So I don't know what has happened to that prize money. And he also didn't bother to publish it in a journal or anything. He just uploaded it on the internet. And then for various reasons, being a strange person, he did not follow this up anymore. Next slide, please. There's another wonderful new branch of science, if I might call it that, or mathematics, or something which is neither physics nor mathematics, or both at the same time. And this is called theoretical computer science. Now, a computer is what I'm talking to you on, right? We are all having laptops, internet. So what is a theoretical computer science? I mean, is a computer theoretical or the science theoretical? Well, anyway, it is a respectable branch of mathematics, very famous, a lot of great people work here. But I've never figured out the difference between theoretical computer science and mathematics. If one of you finds out, please let me know. So they also work with essentially the same objects as many mathematicians. For instance, graphs, how to connect points with straight lines and straight lines with points, and to see if 2 given graphs are the same. Now, a simple graph, you can, by inspection, you can say whether 2 given graphs are the same or not. But we are talking about graphs here where you can have many different cities, many different airlines connecting those cities, for instance, hundreds of cities, thousands of flights. That would also be a graph. So if you want to solve these problems, you have to put them on the computer and have an algorithm that allows you to find, let us say, the most optimal way of traveling between any 2 cities. So I'm just trying to give you a motivation of how a problem that you can write down on the blackboard can become a problem to be put on the computer and can also have major economic consequences, right? Scheduling of flights, scheduling of trains, or for instance, scheduling of raw materials that are produced in one part of the country, shipped to another part of the country, then turned into, the finished product. Then it has to be sent to shops where you and I either buy it or order it on Flipkart. All these are problems which essentially have a mathematical basis, but are realized in real life and have economic consequences also. So there is a bunch of very important problems in theoretical computer science that I have listed here for you, but I'm not going to talk about them. These PDF files will be available to you, something that each one of you can use and probe a little more for yourself. Next slide, please. But I want to talk to you about one of them. One of those problems that I'll talk about, which is the Cadison-Singer conjecture, is based on a notion that is called a Ramanujan graph. Now, Ramanujan is one name that is known to every one of you. In fact, it's the 100th anniversary of his demise this year, I think. As you know, he was a freak of nature, almost. Why do I say he was a freak of nature? Because there was nobody before him and nobody after him who had his kind of abilities to do mathematics in such an amazing way in which he did, through insights, through the way in which his brain was able to sort out mathematical problems. So there are some things that he invented and discussed in passing that are today called Ramanujan graphs. He never named it after himself and say, woke up one morning and drew a graph and say, hey, this is going to be a Ramanujan graph. No. People, others after him have named it a Ramanujan graph. Next slide, please. So this is an example of this Ramanujan graph. So this came in handy for a solution of a problem 2 or 3 years ago, which has its origins in quantum mechanics, and it's a problem in linear algebra. Now, linear algebra is something that we do in St. Paul's High School. It is the simplest example being two straight lines, and where do they intersect? X plus y is 3, 4x minus 3y equals 16. And then you can ask where these two lines will intersect. That's a very simple example of a problem in linear algebra. But if you have more variables, x, y, z, so on, they define planes, hyperplanes, and higher dimensions and so on, right? So you can also have an idea that these variables can even be infinite number of them. So how do you solve these problems? So these three fine people, one of them even of Indian origin, Nikhil Srivastava and two others, they use these notions that were known to Ramanujan in some way. And then they did a lot of computer simulations, and then finally they were able to solve this particular problem. I also want to quote this guy, Nikhil Srivastava, who's of course much younger than me, a little later, because I don't want a situation where I'm only quoting people who have been gone for 50, 60 years. Next slide, please. How am I doing for time? Pranay, I'm doing all right?
Yes, sir, no problem.
Okay, thank you. So let me talk to you about the psychology of discovery. How as human beings, we make discoveries or we think about things. Every one of us, irrespective of what field, what sphere of life we are in, there are times when you get a flash of inspiration about something that you've been thinking about. This happens for chess players, this happens for musicians. Some tune is buzzing around in your head and suddenly you know how to make it better. Or if you're a painter, you're looking around and playing, suddenly you know how to do it better. So let us see what some of these great scientists have said about their Eureka moments when everything came together. So this is what Henri Pankaray looked like. He was a man with rather poor vision. And that's one of the reasons why he was very interested in mathematics, because he could do things in his head without having to read too much, I suppose. So he is often described as one of the last universalists before mathematics broke up into many other subdisciplines like number theory, algebraic geometry, so on and so forth. So he describes his Eureka moment as to how he was thinking about a problem, which is something called the Fuchsian system of equations. So he said that he was just stepping onto a bus and suddenly the solution to a problem, very complicated problem he was working on, suddenly flashed on him. So this is something that every one of us practicing scientists hopes that someday this will happen to you also. I have also had one or two such examples, but I'm not going to talk about that unless asked. Next page, please. Next page, please. Another example of Eureka moments. Somehow many of my examples seem to come from the late 19th century, probably because at that time, science was more of a romantic pursuit and people talked about how they did things. Today, everybody is busy either, printing out their boarding card, or they're busy writing their next proposal, or they're writing a letter of recommendation for the student. They don't even have much time to think about what it is that they're doing. Now, Auguste Kekule is somebody that all of you know about because this is taught in school. All of you know what is benzene. It's C6H6. But at the time when many of these hydrocarbons were discovered as part of the process of the Industrial Revolution and development of chemical industry, more and more substances were isolated, their properties were understood. Today, we know what C6H6 looks like. It is what is called resonant structure. And we know that there's a resonance bond in there, and it looks like a hexagon with carbons at each one of the vertices of the hexagon and hydrogen attached to each of these. But we know also the valency of carbon atoms. And we know today, because of Kekule, that this fourth bond keeps oscillating, goes back and forth between them. But how did he figure this out? Because it was something completely unusual, because everybody was used to linear molecules or what we call aliphatic compounds, I guess, in contrast to aromatic compounds that we have in chemistry. So he said that he has kind of fallen asleep. I think he had also fallen asleep, probably in front of a fire, because those are all very cold countries. He came from Bonn in Germany, rather cold country. And suddenly he had this dream where he saw a snake gobbling its own tail. Isn't that amazing how the human mind works? That to figure out the structure of benzene, he had to see a snake gobbling its own tail, and that's how he figured out the resonance structure. So this is the moment that most people work for. Now, Max Planck is again a name that many of you know, is also a very great figure. He is one of the few scientists who actually even stood up to the Nazis during the Second World War. Very tragic life. I think one of his sons was killed for some plot against Adolf Hitler. So this brings in again the human element that you have to deal with the real world in your life, with your family, with your situation, and so on. And you have to be able to think about science and concentrate on science. So he is the originator of quantum mechanics. It was a complete break from all of human history, where it was only classical physics. And in the year 1900 came the leap because of Max Planck. So you can think of the kind of historicity of his achievement. He was already 40 at the time, considered a little old for having done anything very fundamental, but hey, it was a good counterexample. So he says the outside world is something independent from man, something absolute. And the quest for the laws which apply to this absolute appeared to me as a most sublime scientific pursuit in life. So this is to say that you know that human beings are driven not just by religion and this and that, but there's something innate that we ourselves are a part of nature, that human beings reflecting on nature and laws of life is a part of nature. See, it's a kind of self-consciousness of nature, that we are at the same time different, but also part of nature. Next slide, please. Some others have written about how creativity takes place. Now, if you look at this, it seems like one is talking about science, but this is not the case. This would also be true if you're a lawyer. This would also be true if you're an artist. So Jacques Adama and Hermann von Helmholtz are people who were theorists. Even though they were practitioners of science and mathematics, they also thought about the process by which science takes place. And this is independent of history, geography, which country you're from. Okay. So just because these are figures from 19th century or 20th century Europe, it doesn't mean that those ideas do not apply to you. They apply to you as it applies to me. So there's a phase in which there is a preparation, you're learning and learning, and then your ideas are incubated. And finally, you have the breakthrough, you get a light, that's illumination. But then the scientific process also requires you that whatever is your theory, your idea must be verified. Okay, this is an important point. So here's an example again from Planck, where there were two formulas which are also taught in school. One is called the Wien's law, and other is called the Rayleigh-Jeans law that I forgot. That Planck gave a universal formula which in two limits would give each of these, you see. So all those ideas that are listed in the previous line are realized in this. And within 2 months, Planck made the revolutionary. First, he wrote down his formula. He didn't know where it comes from. Then he had to make this breakthrough and say that classical physics is not good enough. We have to reconcile the two classical limits. Next slide, please. Yeah. So this is what Einstein says about how he had this Eureka moment. So remember, Einstein used to work as a clerk in the patent's office. So he did most of his work standing up because he was not allowed to really sit. So that is why you see pictures of him, you do his calculations sitting. But here he says, I was sitting in a chair in the patent office at Bern. I guess his boss was not looking, so he's sitting in the chair. Then all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. The simple thought made a deep impression on me. It impelled me towards a theory of gravitation. And this is how his general theory of gravity came into being. Subramanian Chandrasekhar, great physicist of Indian origin, he passed away in 1995, I think. So he basically lived in the entire 20th century. He's also a Nobel laureate. So he says, in some strange way, any new fact or insight that I may have found has not seemed to me as a discovery of mine, but rather something that had always been there and that I had chanced to pick up. So that's Chandrasekhar. Next slide, please. So this is a very famous picture of some of the greatest scientists of that era. It comes to the Solway Conference. So you can see Lorentz with the white beard, and you can see Einstein in the middle of these two pictures. And next to Lorentz is the only anomaly in this picture. And in what way is it an anomaly? Can somebody tell me one guess as to why the person next to Lorentz was not Einstein? Why is it an anomaly? Well, I don't think anybody will get a chance to speak now. Well, it's the only woman in this picture, and that is Maria Sklodowska, also known as Marie Curie. So this was in the 20th century. It's a very different thing today. So that is another point that I want to get to as I move on in this talk. Next slide, please. So Nikhil Srivastava, again, I don't want to read out too many things, but he talks about what it is like to be an active scientist. The last two lines is what I'll read out for you. So he says you have to work very hard thinking about a problem. He says you should fail in different ways. You shouldn't give up until you keep trying. But if you know you have tried everything and you are still failing, then it may be time to give up and move on to a new problem. So what he's trying to say is that you have to work hard, but you also have to know where to draw a line. Next slide, please. Now, most of the things that I've talked about so far have been from physics, but there are so many other phenomenal discoveries. So let me enumerate some of them. This is my choice. I'm sure that you have many other choices. Theory of evolution is one of the greatest breakthroughs in science, right? Also based on phenomenological data of fossil finds and so on. It's not like you get these evolutions without knowing something about the real world. Many of the things we have to know. Now, Mendel's theory of genetics is really another amazing thing. Now, Gregor Mendel, as you know, he was a priest in Austria, and he experimented with peas. And he made the discovery that inherited traits come from parents, and he was also able to find quantitative laws in simple systems. Of course, today we know human beings, we have 46 chromosomes and how we inherit traits from our parents and so on. Of course, it's not predictive, but there is a lot of progress compared to the time of Mendel, and it can also help in medicine and so on, predicting diseases, things like this. Continental drift, I think, is another very great scientific discovery. The idea, and this was some Swiss geologist, I don't know much about this, is another very great discovery. The idea that all continents were together once, and it was called Pangaea, and Pangaea broke up into these many pieces. Now, if you cut up all the continents and Madagascar and all these things, and you try to put it together as a jigsaw puzzle, you will see, yes, there is some sense to this continental drift. So science can also be learned this way by experiments, playing around with hands. Ice ages, that's another amazing thing, that there should have been ice ages. Actually, today we live in something called a rather warm period in the climatic history of the world. On what scale? On the scale of about 100,000 years. Not on the scale of millions of years, but on the scale of hundreds of thousands of years. There's something called Milankovitch forcing, which is another phenomenal idea that because of the motion of the Earth around the sun and its own motion around its axis, the precession and the nutation of these axes, that climate can change. So Milankovitch had this idea, and he had very sparse data, but he put it together and he was able to argue from physical laws the kind of seasons that you can have on large time scales, climatic change. Not the local climate change because of stubble burning, but climatic changes because of the motion of the Earth's axis. Now, Pasteur's theory of microbes, what a phenomenal idea that both the curds that you eat as well as diseases are both caused by the same underlying mechanism of microbes. There are other less known things, probably like Shannon's information theory, which is today also needed for the communication we are doing right now, the kind of packets of information that flow back and forth. There are many other references for biology. You can look at this book, The Eighth Day of Creation. Next slide, please. Charles Darwin on his theory. Just look at these words, how beautiful it is. So Charles Darwin always had a beard, I guess. even when he was a baby. We don't have any other photographic evidence. There is grandeur in this view of life with its several powers, having been originally breathed into a few forms or into one. And that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, more beautiful and most wonderful, have been and are being evolved. So there's also this idea of beauty in science. You see, we are motivated as human beings to look at beautiful things as aesthetics. It's not really in the domain of science, but you as a human being, when you want to do certain things, you're attracted to a certain walk of life because of non-rational reasons, like something that attracts you. Next slide, please. So as I said, almost everything that I've talked about have been discoveries by men. Now we know that women are the largest oppressed, not even minority, because statistically women are about 52% of the population. Largest oppressed majority, and even the time when I was in St. Paul's, it was a boys' school. Today I'm pleased to see that it is a co-ed school, as it must be, because these are all things we do as human beings, not because we're men or women. For instance, how many of you know that what is today called computer science was actually created and established by a woman, Ada Lovelace? Her name was Byron, the sister, I think, of or daughter of Lord Byron, the poet. She was, in a sense, the founder of what you call computer science. Modern algebra, not the root system that we read about, in classic books, but the modern version, was also founded by a woman, Emmy Noether, who also had to leave Germany during the Second World War and move to the US, settle down. Marie Curie, who I mentioned. And finally, here is the answer to the question on my second slide. Who was that woman? Her name was Cecilia Payne. And she is the one who analyzed the relative abundances of matter in the universe, how much hydrogen, how much helium, all these things. So she's the one who tells us what we are all made of. David Hilbert, who I already mentioned, in the year 1900, he enumerated 23 problems for the International Congress of Mathematicians, the first international congress, called the Hilbert problems. And the 10th one was settled by a woman called Julia Robinson. It has to do with properties of certain equations, Diophantine equations, again, whole number solutions. So the same idea recurs again and again. Now, all of you have heard of something called dark matter, which keeps galaxies together. It was also found by a woman, indirectly, Vera Rubin. And the other tragic story that we keep hearing, the discovery of the pulsar, was due to Jocelyn Bell. She's the one who made the discovery, but the Nobel Prize went to her thesis advisor, Anthony Hewish. That's how it is. Many of you know the double helix of the structure of DNA. There was a Nobel Prize to Watson and Crick. But presumably, if Rosalind Franklin had been alive, she also probably should have been awarded the Nobel Prize. She made path-breaking discoveries. So did the Indian scientist G.M. Ramachandran. He also had path-breaking discoveries. Now, most recently, Miriam Mirzakhani was the first woman to win what is called the Fields Medal, which is the mathematical equivalent of the Nobel Prize. Unfortunately, she passed away not even 45 years of age. And CERN, the European laboratory that I had mentioned, has a woman director general. Next slide, please. So these are what women scientists look like, just like I had to show you what men Nobel Prizes, they look like us. Any one of us could look like this. That's Emmy Noether on the left, and Mariam Mirzakhani is from Iran, but settled in US at the time of her demise. This is Fabiola Gianotti. Next one, please. Let me also say a few words about our own countrymen. What is it that we have done? Many of these names you know, Ramanujan, who I mentioned. All of you know the Raman effect, of course. Is there some noise in the background? There is a musician on the street. Does it disturb? No, it's okay.
No, sir, it's fine.
It's fine, okay. Then you may have heard of Meghnad Saha. There's a famous ionization equation named after him, the equation of state of stars, for instance. Satyendranath Bose and Bose statistics. We all know about Homi Bhabha and his contributions. Then there is A.K. Rai Chaudhary, who had some fundamental equations in relativity, which were necessary for Penrose for his Nobel Prize, for instance. Ramachandran, I already mentioned. Then there's a very important field called paleobotany, in which Birbal Sahni has very important contributions. Then Janaki Ammal, who contributed to cytogenetics. There are many books written about these people by Venkatraman, which I would recommend to you. Next slide, please. But most of the figures that I mentioned are from a somewhat earlier era. I must say that all these stories of individual romance that all of you know, things have changed after independence. Now science is really a profession and we have international standards. There are many opportunities for kids like you. All the IITs have programs, the ICERS, Indian Institute of Science, Education and Research. Now I think that some parents may also get hold of these slides so they can look up these things to advise their children what kind of scientific opportunities are there. There are other first-rate institutes like NICER in Bhubaneswar, Chennai Math Institute, IISc where I work, many universities. Hyderabad University has a 5-year integrated program for sciences and others. Many of these things that you can explore. But one of the things that I find is almost nobody talks about what they actually do. Very few scientists in India actually talk about themselves, their own work. Maybe our culture teaches us to be very humble and modest. So there are as such not too many role models, except the people on my previous slide who are from a different era. So what do today's scientists look like? Well, some of them look like me. What can I say? So it would be good to explore this in detail. There is a very nice story about primality testing, which was done by Manindra Agarwal, former Deputy Director of IIT Kanpur, how he, along with the students, settled a very important problem in theoretical computer science. It's a nice story of how they did it and so on. One of my senior colleagues now retired. He discovered something called the nuclear Overhauser effect in biological molecules. And he has written about the kinds of things he had to do. How over a Christmas break, he got time to work on a machine because nobody else was there. And it gave him time to figure out this phenomenon. Next slide, please. Now, it is not just me who talks about all these things. Let us look to some expert, somebody who is very successful, who also talks about what it is like to do science, what kind of career it is, and so on. So here is an example of Venki Ramakrishnan, who is often in the newspaper. He also visits India often, although he lives in the United Kingdom. He won the Nobel Prize in 2009. So he made a statement saying that you have to work on hard problems. There is no other choice. And he says it takes courage to work on hard problems. But he thinks that it should not be a contest. Okay, you do it for its own sake. This is something that is emphasized by experts again and again. You don't do something because you want to win a prize or you want to beat the other guy. Of course, it is competitive, but you have to be interested in something for its own sake. This is something that Ruskin Bond also has said about writing books. So this is also universal. But one of the things I think that is needed today, which is very hard, is you have to know many things and you have to have in-depth knowledge in many different things, multidisciplinary training. For instance, Venki Ramakrishnan was trained in physics. Later, he moved to biology. He also knew some mathematics. He could take many things and put things together. It's a challenge and you have to be lucky. But what is luck? This is something that not many will tell you what is luck. But somebody from 2,000 years ago said, what is luck? Luck is what happens when preparation meets opportunity. This is something to keep in mind. That you have to keep working, and when you get a chance to do something, it happens. Next slide, please. So Robert Wilson, he was another leader of science. Now, he was called by the United States subcommittee on whatever budget, so on, say, you want to do an experiment, you want to build a new facility. Why don't you tell us what it has to do with military This is something that every country will ask. Even today, if I want to go and tell the government I want to open a new laboratory, they will ask me, what is it good for? He said this, which is again universal. So I'll just read out part of it for you. It has to do with, are we good painters, good sculptors, great poets? I mean, all about the things we really venerate and honor in our country and are patriotic about. In that sense, this knowledge, he's talking about basic science, has all to do with honor and country, but it has nothing to do directly with defending our country, except to make it worth defending. Such beautiful words. But sadly, the senators and politicians were not convinced and his project was not sanctioned. I hope the younger kids have better luck when they put forward their ideas. Next slide, please. Yeah, I want to say a few words. I don't want to say too much. These slides are there for completeness, for your reference. In science, like in most other spheres of life, communication is very important. When you do some work, you have to be able to explain it to others. What is it that you're doing? So this is something that I wanted to just share with you. I won't go through this in great detail, but writing is very important. This is a skill that in St. Paul's we are taught very well. I have many of my friends from school who are all excellent writers. Okay, so to be able to write research papers, all these things is a great skill that you have to develop. Of course, it's also true in law. It's also true in literature. But even in science, it is very important. It is the imparting or exchanging of information that is very important. So your message, whatever it is that you're trying to say, you have to say it very clearly without ambiguity, without leaving too much space for misinterpretation. Everything has to be clear. And you need utmost integrity in science, okay? Because in the scientific method, you will be caught sooner or later if you're saying something that is not true. Reproducibility is very important. You also have to be able to give credit to others. Supposing I have borrowed an idea from you during discussion, I have to have the grace and the manners to acknowledge that I got your help. Next slide, please. So these are things that you need to keep in mind. Also in speech, and science being an international effort, you have to be able to talk in a language that is free of your own immediate cultural surroundings. You have to be able to speak in a way that a person from a different culture doesn't misunderstanding. You must have, brevity of expression. You must have a very clear way of talking, simplicity. So one cannot also overemphasize, and let me say this, the importance of the English language. In St. Paul's, we are taught to speak and write excellent English. It's a great asset if you're able to express yourself in English, something to master and keep in mind. Grammar, pagination, and punctuation, all these things are very important. We can't just go to Grammarly and say, write a paper for me. It doesn't work like that. Okay. So this is something that I wanted to put down as a takeaway for you. This is just, distilling my experience of a very long time. Next slide, please. So let me finish with a little bit of practical advice for each one of you. This is something that I tell my students, that you have to master a subject. Because if you're trying to kind of wriggle your way out of some situation, whoever is a listener will figure out that you don't really know what you're talking about. We have to be also extremely honest. And here is something which is cultural, because we are not taught this. Supposing you're asked a question to which you don't know the answer, you try to hazard a guess. Oh, maybe it's this, that. Far better to say, I don't know the answer. Give me a chance to go and find out what it is. This is also true in most spheres of life, even more so in science. Okay. And don't hide details of how you came to an answer. Be upfront. In the long run, that is what will help you. Should not be secretive, should not tell half-truths, and so on. Acknowledgements are very important. And finally, develop very good work habits. Keep an online diary or a journal where you write down things so that it helps you manage your own time. Okay? So this is the kind of advice that you would need. Again, in any sphere of life, but I'm emphasizing this for science. Next slide, please. I think I'm more or less coming to the end of my talk. So my advice to you, because today is one day that I have a chance to give some advice. I don't want to lose it. So follow your hearts. Don't only think about career, the next $100,000 or the next job that you're going to get or the next whatever, because we are dazzled with these stories of Sundar Pichai and Satya Nadella earning $200 million, so on and so forth. Good for them. And we wish them well, but not everybody has to do that. Not everybody has to be a doctor or a chartered accountant. We need some people to do science also. There is more than fun in research and discovery. It's a very rewarding career. It's difficult to find the correct fit, but it might help. And in the final analysis, if you are going to be doing research, you will be open the doors to a new tomorrow for the future generations. It also requires a lot of patience because the subject is already very complicated. It's like running a marathon. I've already quoted Edison, so I don't want to repeat that. So here is an article that I also want to refer you to about how to do your research. It's for more mature people, not necessarily school kids. Then I want to finish with this, almost finish with this quote, again from Chandrasekhar. Not everybody can be an Einstein, not everybody can be a Watson or a Crick. But this is what he says. He is humble because he is himself one of the greatest. But he says, the pursuit of science has often been compared to the scaling of mountains, high and not so high. But who amongst us can hope, even in imagination, to scale the Everest and reach its summit when the sky is blue and the air is still? And in the stillness of the air, survey the entire Himalayan range in the dazzling white of the snow stretching to infinity. None of us can hope for a comparable vision of nature and of the universe around us. But there is nothing mean or lowly in standing in the valley below and awaiting the sun to rise over the Kanchenjunga. Next slide, please. Which is my last slide. I want to say here that I always try to remind myself these words of David Hilbert, which now appear on his gravestone. In German, it reads, Wir müssen wissen, wir werden wissen. We must know, we will know. So let me stop my formal presentation with these words and we go on to the next stage.
Good morning, everyone. Thank you, sir, for sharing and enlightening us with valuable knowledge in the field of space, particle physics. You have covered a lot of aspects. Thank you so much, sir.
My pleasure.
Yeah. We came to know about the struggles of all these scientists or mathematicians or anything. So we have a group of students here who are very, very curious and they would like to put a few questions to you, sir. They would like to interact with you. Come on,
Good morning, sir.
Good morning.
So, my name is Amartya, sir. So, by the end of 10th grade, we all like many subjects. But how do we know we have a flair in science or we are into sciences?
Okay, so that is the reason why, for instance, the University of Hyderabad program does not ask you to specialize very early. I don't know the precise steps, but the first couple of years, as far as I know, are a common syllabus, irrespective of what your branch would be, so that you find yourself when you're a little more mature. As I said, it's a matter of what attracts you, right? So this is a voyage that every one of us has to undertake. It was the same voyage for me. Why exactly did I take this ship to sail? I myself don't know. There are so many factors. One is your own natural talent, ability. Ability is also important. I may really love number theory, but I don't work on number theory because maybe it's too hard. Maybe I don't have the aptitude. So this will come to you. There is something called scientific maturity that you yourself will discover when you're mature. It's like this, you're working on puzzles. You do Sudoku puzzles, you do chess puzzles, so on and so forth. One fine day, you wake up and suddenly you see the patterns. Okay. That's the nature of cognition. That's the nature of knowledge. That's the nature of the human experience. It's not something that is algorithmic, that I take you and I put you into a machine and out comes a mathematician. It doesn't work like that. Okay. So you have to keep working on it, and it's your own individual, striving, which will take you to your goal. As a society, we can only provide the necessary facilities for such a thing to happen.
Thank you.
Are you satisfied, or you're just being polite?
Yes, very, very satisfied, sir.
Thank you.
Good afternoon, sir.
Good afternoon.
I'm Shahana, and my question is that the law of conservation of mass states that matter can neither be created nor destroyed. So how exactly did the universe begin?
Right. So that is in classical physics, right? So in quantum physics and in the special theory of relativity, we know that that's not true, that energy and matter are interconvertible. So that's the principle of all these high energy experiments also. Take electrons and positrons and collide them, it forms a ball of energy, and then the energy produces particles, which are not what you started out with. So this law that we learn in school is the classical laws as Newton saw them. And now it's replaced by this other picture. But it's an approximation. It's only under very special circumstances that we can have this kind of interconversion going on. The sun produces energy, right? How does it do it? The solar cycle is there. Hydrogen is turned into helium and produces energy, right? And then in the mass defect between hydrogen and helium is where the bulk of the energy is produced. There's a whole solar energy cycle in which various atoms are changed, the nuclei are changed, and nuclear fusion takes place. And that's the principle.
Thank you.
Good morning. Good afternoon, sir.
Good afternoon.
My name is Brinchi, and I have a question to ask you. There is a theory that states there are infinite number of realities in our universe called the multiverse theory.
Yes.
So, do you think that in the future can humans travel between these realities?
Well, as you yourself said, that this is a theory. It has been put forward by people who work on a branch of science known as string theory, and it naturally leads to this picture of multiverses. But it's not verified yet. We don't know if it is really true. These are all beautiful ideas. It's also a big playground of ideas, right? Elementary particle physics, field theory, all these things. So we have to, this is what we call blue sky research, where research doesn't immediately have an impact like 1% improvement in the baud rate for us to watch Netflix movies, for instance. This is, science at the frontier where clever people who are very good at maths, physics, so on, they are thinking about various unsolved problems of physics. So tomorrow, if there are multiverses, you please go to another universe and send me an email from there and we'll see. Okay?
Good afternoon, sir.
Good afternoon.
Sir, my question is there a possibility of a multiverse that is made up of other than matter, like antimatter or dark matter?
And this is a very important question. In fact, in this Big Bang, forget about multiverse for now, but let's only think of our own universe, okay, which came from the Big Bang. Now, supposing at the time of the Big Bang, there was as much matter as there was antimatter, how is it that we have more matter today than we have antimatter? Okay, so that's also a hypothesis. We don't know for sure whether in the beginning there was a symmetric universe between matter and antimatter. But let us assume it was. Then how did this net matter build up? So Andrei Sakharov, who's again a well-known scientist from Russia, he said that there must be three conditions must be met before a net matter is built up. And he said that first of all, there have to be interactions which violate matter-antimatter symmetry, and different kinds of interactions which violate conservation laws for matter. And there has to be a departure from thermal equilibrium, that you must have a buildup of a net matter asymmetry. There may be a copy of the universe where it happened in the other way also. But how do these two communicate with each other? We don't know. These are all very beautiful ideas, but your guess would be as good as mine to answer this question. Okay.
Thank you, sir.
Good afternoon, sir.
Good afternoon.
Preetham, so I have a doubt that there have been few discussions that if a particle travels with the speed of light, it may do a time travel. Is it possible to do so?
No, not really. It is not, so far there's no evidence that that can be done. Okay. So the speed of light, actually it's a property of space-time. Massless particles travel with the speed of light because light is the first massless particle that we came across. Now in this gravitational radiation, there's one more prediction of Einstein's theory of relativity, which is the existence of particles called gravitons. They have not yet been seen because they interact so weakly that it's very difficult to actually observe them. But any other particle which has a mass, it cannot. Within the known laws of physics, it cannot. Okay.
Thank you.
Good afternoon, sir. So
Good afternoon.
today I have a question about choosing a career. People say that you need to talk to your parents about your career because they know you better, and on the other hand they even say that you should listen to your heart, like you also said it before, like you should listen to your heart as you know your abilities and disabilities yourself. So, but if we listen to your heart and you are not successful, so people then speak about that you were not successful, and we said you to listen to your parents. And if we listen to our parents and do not get successful, they even say that we said you to listen to your heart. So,
What can I say? I have a daughter who's a little older than you. So she is finishing her, she's just finished 3 years in engineering college. She has 1 more year to go. She likes what she's doing. She likes biotechnology, which is what she's studying. She's also interested in biology. But you have to get a basic degree, okay? And after that, you can try to do what you want. There are so many options available. There is Open University, there is colleges. Supposing you take up something that you really are not interested in. I don't want to name any particular discipline because I don't want to be disrespectful to any profession. It's also a matter of individual choice. I may have chosen biology and I was never interested in biology. Then I wish I took physics. Within research also, there are choices like that. No? There are some people who want to settle down very quickly, have an income. Depends on your family situation. Supposing you have parents who are not very well off and you have to support them, you have to get a job. You see, life is not perfect, right? Everybody is faced with reality, with their circumstances. But if you don't have that kind of pressure, you also have to think about your happiness and your joy, okay? This is what I can say. This is what anybody will say. The only thing is to do well in any sphere of life, you need a lot of patience. It's not like, that you get a job and within 6 months you become a great expert. No, it's not like that. Anything like requires a lot of work. Okay? I mean, I've given you a very general answer, but more than that, I cannot say unless it's a student about who I know something and then I'm able to advise them.
thank you, sir.
So one more. Yeah.
As many, I have no problem. I'm not yet hungry, so it's okay. Maybe the kids are hungry. Hello, good morning. Yeah.
I'm Anam, and my question is that how can I stay true to my career and not get distracted from it?
That's a question I ask myself every day, and I haven't found the answer. No, but see, you have to be truthful. All the values that you learn from your parents, from society, from the school, is what you also apply in your career. You don't go and you fudge a number. Supposing you're working in a bank and you make, just put a white out and write something. You don't do that, right? So similarly, if you're a doctor, you know that your patient is about to have a heart attack. You don't say, oh, go home, you'll be okay, right? So it's a matter of integrity. It's a matter of honesty. So being faithful to your career is like being faithful to your parents or being faithful to your friends. This is all human experience. Career is one aspect of it. I don't think there are any exceptional rules to career compared to any other sphere of life.
Thank you, sir.
So thank you so much, sir, for answering all the questions. Okay.
Were they reasonable answers? You have to tell me. Yeah.
Definitely. Yes, yes, yes. Yeah. Answering all the questions. Okay.
Were they reasonable answers?
Definitely.
Thank you, sir, for that enlightening interactive session with the students and enhancing their knowledge. Your presence is highly motivating and inspiring to our young students who are looking forward to lots of sciences in their higher studies. Let a new India arise out of these students who are the future, hope, and promise of the nation. May I now invite Sri Kanaka Kumar, Treasurer, Alumni Association, to propose the vote of thanks.
Thank you, everyone here. You know what? First, I must thank all of you who have. Hello. Hello. I must thank everyone who has come down here, and it was an intelligent lecture from one of our own Gaudian scientists. Thank him for having taken his time and come down here. To all the young minds who are here, I appreciate that you have all appreciated his speech, and now it is my turn to thank everyone. From the guest lecturer, Professor Subramanian Ananthanarayan, Ananthanarayan of the IIC, Bangalore. Thanks to Brother Rayapareddy for taking all the pains and pleasure of having made the venue of Alfonso Hall to receive this. I also give my thanks. Thanks to Swarna Gauri teacher for introduction, guest speaker. Thanks to Padmaja teacher for managing the question and answer session. Thanks to the students and alumni for watching this program live from our school premises, and alumni all over the world who would be on the YouTube channel, Facebook, and other links provided. Thanks. Thanks to our in-house tech support by the alumni members. Thanks to our moderator, Pranay Rupani, for conducting the proceedings. Thanks to Frederick, Luhar, Madani, and all other staff of the school for the excellent arrangements that have been made today to make this program a grand success. My thanks once again to all of you sincerely.